Okay, now it's really time to start. So I'm happy to see so many people here, and it's of course a great pleasure for me to organize this workshop, Optimization at Work. The first speaker of today's workshop is our guest from, I don't know how to say, from at least 3 different countries, probably. From KAUST, which is in Saudi Arabia, from the University of Edinburgh, which is in Scotland, or United Kingdom, and originally you are from Slovakia. But now you are also our professor, visiting professor at Moscow Institute of Physics and Technology. And here Richtarik is supposed to speak about stochastic primal-dual hybrid gradient algorithm with arbitrary sampling. Thank you.
So thanks a lot for inviting me over here. So the last comment will be correct once I sign the contract. I hope it's already here. So it's not yet fully correct, but today maybe it's going to be correct. So it's very nice being here in this different weather, as you may imagine, from Saudi Arabia, where it's very hot. This is a very welcome change after some time. So I'll be speaking about a stochastic variant of an algorithm, which has a very long abbreviation and a strange name, primal-dual hybrid gradient method, also called, known as Shambol-Pock algorithm. And the stochastic version means that we introduce randomness somehow into the algorithm to hopefully speed things up. Shambol-Pock algorithm, or a primal-dual hybrid gradient algorithm, is very famous in imaging community. It is very versatile. It applies to many problems under all kinds of settings. Whether you have convexity, strong convexity, Lipschitz continuity of the gradients, essentially it applies to functions which are convex, closed, and proper, as we will see. And the idea here is to analyze the method, design it, analyze it, and then to apply it to a bunch of applications. And one of those is the PET reconstruction. So I'll talk about this now. So this joint work with several authors, Antonin Shambol, 2 authors at Cambridge, Matthias Erhard, Karl Bibiane Schönlieb, and some people from London. So let me first ask you, I want to know, how many of you are familiar with the Shambol-Pock algorithm? Is that 0? Is that 1? Okay. Is it 1/2? Okay. My French is not that good. All right. So the talk is based on these 2 papers, but I'll mostly speak about the first one. That's the one where we establish the theoretical part, do some computations, but those computations are done on artificially constructed problems. And then the second paper is where we apply this to actually real data from PET scans. So the motivation. Now, for a while, I'll talk about stuff which I have no clue about. Okay, so if it looks like I'm not making any sense, it's not because your English, is not that good, or it's because I just don't know what I'm talking about. So here is a PET scan. I've never been in one. You can go inside. There's a fancy image. It's a fancy camera, really. So you just thrown in there, and something happens, and they will be able to see what's inside you. So there's a radioactive tracer that is put inside, and then some stuff happens, which I don't really know what's going on. So there's some positron annihilating with electron, I believe, some gamma rays, and so on, emanating in opposite directions, and then being caught here at this ring. And you want to reconstruct the image based on those rays there. Okay, so probably already made some mistakes there. So the idea here is to come up with a physical model that somehow captures what's going on. And the basis of this is this X-ray transform. Now, this will be a very simplified model just to do a line integral across a line perpendicular to this vector S here. you have to do something more complicated if you want to have a realistic reconstruction. So there is a linear operator here. It's called MNX, and it is constructed somehow. I'll comment on this a little while, but once you have it, so somehow abstract from it how you get it, but once you have it, what's going on is this, that you apply this linear operator to the image that is unknown, that you wish to reconstruct, and we model that image as a vector, be a big dimensional vector. Plus there is some background, some noise. This could be some scatter information, random noise, whatever. So this is corrupted. And on top of that, what we really observe is just something Poisson from a distribution with this mean. So this is the stuff that we will actually observe. We'll never observe the image. We just observe some property of the image. And somehow from these observations, we'd like to reconstruct the X. And now the A is a composition of the X-ray transform that I talked about before. There's some correction term N and some dead detector modeling M, and these can get quite complicated if you want to have a very good model. But at the end of the day, this is a linear map. Okay, so that's what we're after. Now, here is an image which looks nice, but which I have no clue what that means. So you can talk to some of my co-authors about this. So I just thought I would include it because it's nice. So really don't ask me about this one. I don't know what is this. Okay, so now let's go back to the reconstruction. So here is what we could do. So we observe these Poisson random variables with means lambda i's. Okay, AX plus the background noise. So ith coordinate of this long vector is lambda I. And now we'd like to estimate these parameters lambda i's, or in fact, we'd like to estimate the x's at the end of the day. So what we can do, we can apply this technology of map estimation. So we'll assume that there is some prior on this image, some prior information that we have, and this is the distribution of that prior. And then we have some likelihood function. What is the probability we observe these things that we do observe? And we observe capital N entities, D1 through Dn, given the image. And we would like to maximize this likelihood and say that this is actually the image reconstruction. Okay? So let me pause here. Does this make sense? Okay. So want to ask any questions at this point?
Why do you use Poisson's?
Somehow this is the standard thing in PET reconstruction because of the nature of the process there. But this is something where I don't really see deeply enough into why that is the case. But that is the standard model. In general, you can use anything else, but that's what we will use here. And that's how you get nice reconstructed images out of it. Okay, so this is a problem, but it's still not the problem that we'll be solving using an optimization algorithm that we design. This is still just a motivation into what we'll be doing. So after this, how do we solve this? Well, we have max of some crazy things. We have to now choose a prior, and we have to figure out what the likelihood would be. So if you choose the Poisson likelihood, this is what you're going to get. Okay, so this is just by definition, and this is just by simplification. And what you get in this exponent is a product of these exponentials where you have the KL divergences between the observations and the means, plus some other term, which only depends on the observations. So now, if you plug this back inside here, you get something complicated because it's a product of exponentials. But if you take log, then that doesn't change the maximization objective. And things simplify, the products change to sums, the exponentials disappear, and things will look nicer. So here's just the definition of the KL, the generalized relative entropy. Okay, so you don't have to worry about the actual format of these formulas. That is not that important right now. We'll abstract from that later on. And now what we're going to do, we're going to return back to the problem. So this is the problem. Now we insert a logarithm there just to simplify things. It's an increasing function, so everything is fine. And now these exponentials disappear because you have log of these exponentials, and then the product changes into sum. So now what we're going to do, we're going to minimize sum of all of these functions plus some regularizer g, and that's the log of whatever we had there before. And notice this is sum of many functions, and there's as many functions as we have observations. And these are KL divergences plus some other some constants which actually don't matter because they don't depend on the x. Okay, so this is what we can do, and now to make things more practical, we can put some of these observations together, just group them together, and let's say we have a partition, bi's, of all those capital N observations, and we have n of those, lowercase n of those partitions, and we just do a double sum here. And this complicated term inside, we'll just call it fi ai x. Okay? So this is the abstraction, and in the end, we arrive at this problem. We just want to minimize sum of n terms. Now it's lowercase n, that's smaller. So there'll be n blocks of things. And you have these linear operators, AIs. We don't have to think right now about the structure. These are just some operators acting on the image. And you have some loss functions or fidelity functions, Fi. Okay? So this is one way how you can motivate this type of a problem. And now the issue is, how do you solve this thing? Okay. So the way we'll do this is we'll first assume that these functions Fi's, they'll be convex. G is going to be convex. But we'll not assume anything like, in the beginning, anything like strong convexity or Lipschitz continuity of gradient. We just assume these are closed convex proper functions. And our first complexity result will depend just on that. And then you get refined results based on some additional assumptions. But we will not work with the formulation of this type. We'll actually work with the saddle point formulation because we want to extend the Chambol-Poc algorithm to the stochastic setting, and the Chambol-Poc operates in a saddle point formulation. So let's get there. So first of all, these functions, just to make this a little bit more formal, there'll be functions which are extended real value. They can have values of infinity. And this is very useful for various applications where that can happen. And these yi's, they're just some finite dimensional Euclidean spaces, just some Euclidean spaces. So in the product spaces. So then we have this general space Y, which is just a product of these smaller spaces. And this is where things will work. And you just assume the induce in the product, induce norm, and so on and so forth, so that everything is nice. Regularize the same stuff, but now regularize is going to work on some other Euclidean space, X, and also will be extended real valued. So some examples of this, you can have total variation, total generalized variation. You can have L1, you can have rich regression terms, so the Tikhonov regularization, and so on and so forth. So there's lots of examples here. So this is the one big assumption we have behind everything. So these functions are all proper, convex, and closed. So lower semi-continuous. So if this is true, then for instance, if you look at the ith fidelity function, it's going to be equal to its biconjugate. This is the Fenchel conjugation, convex conjugation. And this is a property which we'll need somehow in the analysis. And this is just a definition of the conjugate of the conjugate, right? Written down there. So once we have this, we can dualize these terms. Because we can take this Fi and write it down in this way. Okay, just Fi is equal to this. And then suddenly we introduce these dual variables, Zi's. And now we have a saddle point problem. So we start here. We dualize these other ones. Now we call these dual variables Yi's, not Zi's. And this is the problem that we actually will be tackling. Okay, so let me pause again. So that was motivation somehow into one particular application, that's the PET reconstruction, and how that leads to a problem which looks like this in its abstract form. And this is the problem we'll be looking at. So I invite you to interrupt me and ask anything if anything is unclear.
Matrix A, capital A is sparse? No.
At this moment, it's really anything. Doesn't really matter. We'll not have those assumptions there whether it's sparse or not. this is, at this abstract level, now we can throw away the motivation. And this is just a problem of this form. This is any matrix AI, any proper closed convex functions, Fi and G. If you have sparse matrix, then some nice things will happen. Every iteration will be cheaper, and there is a potential even for the complexity to be better. So for sparse matrices, the number of iterations might be actually better, which will somehow follow from some of these results. So later on, we'll have some additional assumptions, such as strong convexity of this Fenchel conjugate of these fidelity terms. And we'll call this Mi, these parameters. They don't necessarily have to be positive. If they're just 0, there's no additional assumption. This is just convexity. And that's what we assumed already. The same thing for the regularizer G. Okay? So we'll see these mu G and mu I constants around quite a bit later on. So please do interrupt me. I don't have so many slides, so you have to help me out. Yes?
Where is set Y came from? So they taken from.
Where did the Y come from?
Yes.
Okay, so Y comes from here. So once you assume that these functions Fi's are proper convex and closed, whatever that means, it's going to be true that the Fi's, they'll be equal to their biconjugates. And this is the definition of the biconjugate. It's the conjugate of the conjugate. So you have this equality, that this is equal to this. So every time you see Fi in this formulation here, you just replace it by this maximum. So you're dualizing somehow these functions, and that's where those variables will come from. Or okay, that's what you were asking?
Yeah.
I hope so, yeah. So it seems at this point it's just some technicality there, but these are dual variables. You can think of this from the perspective of Fenchel duality or Lagrangian duality, but this is somehow just a simple trick how to insert additional variable here just by writing in a variational form expression for Fi. Okay, good. So here is the algorithm, but this is the primal-dual hybrid gradient algorithm, so the Chambol-Pock algorithm, in a pretty general form. The basic algorithm didn't have these matrices T's and SI's around, but instead they were just scalars. So somehow there was just a scalar times the identity matrix. Again, scalar times the identity matrix, and then those scalars are the step sizes for the algorithm. A more general one, which was introduced later and I think probably the last paper here, that's the one which introduced these matrices as a generalized version of the original Chambol-Pock algorithm.
You assume that star is Prox friendly.
Yeah. So there are these two Prox terms. This is how the Prox operator is defined. So if you apply the Prox operator to G with some matrix M, what you're doing, you're minimizing a quadratic perturbation of that function G, and the quadratic perturbation has Hessian M inverse. So this is a definition of the Prox operator, and we assume that these G's and Fi stars are Prox friendly, that we can compute these proximal operators easily. Either there's a closed form expression, and in many practical cases there is, or it can be very quickly estimated and so on. If this is not true, then this algorithm will not work well. Okay, so it's not an algorithm that will solve all problems always. So these two operations have to be easy to perform. Now, fortunately, we have some control over this because we can choose the pri, we can choose the regularizer, and in many applications, you have some choice. You're not stuck with just something. So let's say you work with TV regularizer, and you can add L2 regularization to it to make it strongly convex. You can just start playing with these things, and sometimes you arrive at something which works fine in practice, but it's also Prox friendly. The same thing with Fi's. So for the Fi's, remember that we had a way of grouping these things together, and this might be useful. All right, so what's going on here? We take this step in the variable x with step size t, but this is a positive definite matrix now. But think of this as maybe just a scalar times an identity. And then you have the adjoint of the operator a, which was there in the beginning. And you apply this to some strange vector y bar. The strange vector is being updated here in the third line. And then you take the prox of g of that, and you call that xk plus 1. And these dual variables, you update them with the prox of these fi stars. And now, these dual variables, you really have a maximization problem. That's why I'm doing plus something, right? So you can think of this as something like a gradient step minus, and this is plus like gradient ascent or something like that. So, and there the variables are SIs, and you don't have conjugates of those little operators. And then you do an extrapolation step. So you take the difference of the last two y's, and you add that to the last y with some multiple, and somehow even theta equals to 1 works. Okay, so now if you think about the complexity of this algorithm, by complexity I mean just the cost of one iteration, what you have to do, you have to evaluate every single operator AI and its adjoint, every single one. And you have lots of them if you have lots of observations. Let's just go back here. So how many of these do we have? These AIs? Well, as many as n. And s could be as many as the number of observations. I mean, we're doing this grouping stuff. So we grouped some observations together. This is because somehow it will be easier to process things in batch for physical reasons and also for some linear algebra reasons. But still, this n is going to be very huge. And if you do a 3D PET scan, this will be a really, really huge number. So it'll be millions and beyond that. So very large. And you have to evaluate all of them. And that is a bottleneck of this algorithm. If you want to scale it up, you have to do that. It's a lot of work. So even if you assume these prox operators are simple, you have to do these things. And that will be the bottleneck then. And those of you who are familiar already with randomization and optimization, you know that almost every time you see a deterministic algorithm, which works with huge amounts of data, it could be randomized, and the randomized version only works with a random subset of the data in every iteration, and the algorithm will be much faster usually. And it'll be much faster in theory and also in practice. This is something that happens, let's say, with gradient descent, and you generalize this to stochastic gradient descent, and there are applications in machine learning where SGD is just much, much, much faster than gradient descent. The same thing, let's say, with gradient descent and relationship to randomized coordinate descent, and so on and so forth. There's many of these variants of randomized algorithms which outperform the deterministic counterparts. And this is what we are after. So now help me designing a randomized version of this. So now with what I told you, how would you randomize? What would you randomize over in this algorithm if you were to design a randomized Chambol-Poc algorithm?
Before we start to randomize, what is the rate of convergence of this version?
Yes, we'll talk about this. So Sasha doesn't want to randomize yet. He wants to know how this works. So we'll give one theorem, and the theorem will include this as a special case as well, and the randomize as also. So we'll get that rate, and it will be the same rate as established for this algorithm in the original paper describing the algorithm. So help me designing a randomization procedure. What would you randomize over? So you want to randomize over this matrix vector multiplication. Okay, that's a good idea. So, but if we randomize, what does it mean? How would you do that?
You know in advance, for example, that x belongs to sigma x, for example.
Okay, so here we don't know it. We don't have any constraints. We don't have any constraints. So here we cannot pretend that those variables are probabilities and so on. So we cannot quite do that. But we can do something like what you suggested. We'll randomize in a very trivial sense. So remember, you have to do these multiplications here. Let's say, look at this step. So let's just not do it for all i's. Okay? We have to do it for all i's from 1 to n, and n is huge. let's not do it for all i's. Just do it for a subset of those i's. Maybe just 1 or 2 and so on. So we'll just cheat. Okay? Because that is the bottleneck. And if you do it just for a random subset, then you may ask, okay, but then there's this A transpose here, and you still have to do that, and that is a big matrix. Well, if you only update a few of these yi's, if you look at the structure of this y bar, you can actually implement it in such a way that you only apply the AI stars corresponding to the i's that you used. Does that make sense? So somehow, if you do this just for a single I, then you have to do this only for a single AI star. Okay, that is what will happen if you look into the algebra of things. So that seems like a way to go. And that's exactly what we'll do. And there'll be just one change here. So we choose a random subset. So the red stuff is the new stuff. This is the old algorithm, and this is the new one. And whatever is red is the new stuff. So now we choose a random subset of these dual variables. And by random subset, I mean a random set-valued mapping from some distribution that you decide on. It can be anything that you wish. So it could be a singleton. It could be I with probability pi, and pi is some positive probability. Or, as a special case, it could be everything with probability 1. Okay? If it is everything with probability 1, then you do this for all i's, and this p will disappear here, and you get the original algorithm as a special case. But if this S hat contains just a singleton, then you do this prox operation only for one I. So you save a factor of n, and if n is million, then you save a factor of million in each iteration. So it's going to be much, much cheaper. So what is this P inverse here? Well, first of all, this P matrix is a diagonal matrix with probabilities pi's on the diagonal, and these pi's are just probabilities that I belongs to this random set S hat. So it's some sort of a marginal property of this set-valued mapping, of this sampling. So this matrix pi does not describe uniquely this random set-valued mapping S hat, but it's its property. And it turns out that's one of the properties which are important. There is one additional one which is important, and then that's it. And notice, again, as I said before, you only evaluate AI and AI star for those i's which are picked in this set. So here I want to pause again, because this is the algorithm we'll talk about. And I want to make sure that you have some intuitive understanding of it. So please ask some questions. Yes.
Why we need to evaluate I?
Why we need to?
Yes, why we need to evaluate matrix A subscript I?
Okay.
So suppose it comes from the model.
Yes.
What is the step of evaluation of AI? Can you describe it?
Okay, so if you look at the problem here, the problem formulation involves these AI matrices. Okay. So if you abstract from the actual application behind this, because this has many applications, there was just one. AI will typically be some data matrix that you obtain somehow. For the PET, in the PET case, you get this somehow from these observations. But in machine learning, this would be maybe images. It would be vector or matrix representation of some images or some pieces of text or videos and so on. So you have that. And the problem depends on the data that you collect, however you collect the data. So it's part of the problem. And if you want to solve a problem which depends on some data, you have to look at the data. If you don't look at the data, you cannot solve the problem. So you have these matrices around, and it's not a surprise that the algorithm will have those matrices around. It does depend on the data. And by evaluation of AI, I mean you apply the AI matrix to this vector xk plus 1. But that means that you have to touch every entry of that matrix. If it's dense, every single entry. If it's sparse, then not every single entry. But if it's a piece of, if it's a video, you have to actually watch the video. That's what it really would mean doing this multiplication. You have to touch every pixel of every frame. Okay? And that is going to be costly. Exactly, yeah. Yeah. So.
And do you assume that we know function f and g?
Yes. So we know that because this is part of the problem description. This is what we want to solve. And we better know what we want to solve. Otherwise, we won't be able to solve it. So we have to have G, and we have to have Fi. We have to even know what is Fi star. And we have to know its proper closed convex. So we have to know these things that we assumed that we do. And once we have that, this is the problem that we want to solve. So that is part of the problem description that we know. So there's no trick here. Those assumptions I mentioned. The tricky part might be, how do you actually choose this random set here? Or how do you choose this parameter theta? Because this is not part of the problem description. This is the algorithmic parameters coming into play. And we have to do some work to choose them.
We must choose it before.
We choose this random sampling, you mean?
No, I mean again.
Fi's and G's.
F and G.
Yes, that is there before we run the algorithm.
And another way is how to choose a random subset.
Right.
How many elements?
Yes, that's an excellent question. So the way we're going to analyze the algorithm first is fully general, which means it will be analyzed for any random set. In each iteration, you choose this random set from a fixed distribution of random sets. So you decide on this somehow, and I'm not first telling you how. You decide, it's your choice, and then I'll tell you that the algorithm will work. It will converge. But your choice will impact the convergence rate. And then you can do the reverse engineering and ask, how should I have done this so that the number of iterations is as small as possible? And we'll look into this a little bit.
The question is, for example,
Okay, so just to give you some insight right now, is if you have a single processor, because it depends on what kind of computer you have. If you have just a single processor working for you, so not a distributed platform, not a parallel processor, single worker doing all of this, then the smaller the set is, the better. Okay, that is the intuition. You should not choose everything. You should do with as small as possible, which means just one eye at a time. So that extreme case is the best.
but it means that if I choose one subset as,
Yeah.
I receive one solution.
Yes.
If I choose another subset as,
Okay, so here is an answer to the question. These are all excellent questions. So what you do, in each iteration, you choose a different set of size 1. Different, because you have this, think of this random set as a random variable, and you always flip the coin each iteration. So maybe in iteration 1, I choose the first I, 1, and in iteration 2, I choose 3. Iteration 3, I choose 10, and so on. So somehow I randomize over those data points, over these I's, which means that there is no way I will not choose everything at some point in the future. Okay, so you flip things with positive probabilities, which means you'll see everything. Okay, so it's true, and this is very good to clarify this, that we're not choosing the random subset at the beginning and we fix it and we work on that only. No. We choose a random subset, and then in the next iteration we choose another random subset. In the third iteration, another random subset, but always according to a fixed distribution that we decided on. We never change the distribution. The distribution is not evolving. Kind of a stationary approach.
and I use this subset for y and x as
So only for the y's.
no, I mean only for
Only for the dual variables, which means only for the observations. We only randomize.
x, I calculate all distributions. My methods, A.
No. No. So this is something which I commented on before a little bit. So if you do this for subset I in S hat, it turns out that if you want to implement this matrix vector multiplication, you only have to do multiplications between AI stars and some other vectors only for I in S hat. So that also is true, but this is not because I choose. This is not because I changed the algorithm. It's because the algorithm can be implemented that way efficiently without any change. And the reason is because only some vectors in this y bar change, only some part of it, and I don't need to multiply by those things that didn't change. So that's the reason. And it only takes like 2 lines of derivation to show that that is the case. I'm not doing it here. Yeah, excellent.
We can see step size is matrix T,
Yeah.
S, and also parameter theta.
Yes.
How to choose such?
Yes.
Well,
These are all excellent questions.
converge.
Yes, yes. So these are all excellent questions. I'll give you a theorem, and the theorem will say that.
Okay.
At this moment, we have the choice, and we're confused, and we don't know how to choose these things, right? How to choose T, how to choose this, how to choose that, and how to choose the sampling. Too much choice is not good for our health, right? Okay. So let's go to this. So all these questions now point to convergence, so let me go there. So here is a summary of the convergence results here. So one convergence result is if you assume a solution exists, so this saddle point formulation has a primal and dual optimal solution, then under no additional assumptions, just the stuff that we assumed before, which is proper closed convex and so on, the method will have a rate 1 over k. And I give you the specific properties of T and SI and so on, but this is kind of big picture. It will be 1 over k. Now, if you assume strong convexity of both of these Fi star and G, remember Fi star is the function which appears in the saddle point formulation, not Fi, so that's the thing we care about. If that is strongly convex for all i's and both the regularized is strongly convex, then you have linear convergence. So the decay of the error is exponential in the number of iterations.
Am I right that k divided by square root of multiplication mu, this mu, yes? In this power. Conditional number, square root of conditional number, that is, in our case, conditional number is 1 divided by 1 mu.
We'll get there. We'll get there. Yeah, we'll get there. I'll show you the formula. Okay. And then a strong convexity only in those Fi stars. If you have just that, and G can be anything. And this is important because maybe you work with a TV norm as the regularizer, and then you're in this setting. Then you get accelerated rate, 1 over k squared, but you have to modify the algorithm. You cannot work with the original one. You have to do dual acceleration. And you can do the other way around. If G is strongly convex, then you can do primal acceleration, and then you get 1 over k squared. Okay, so this is kind of the big picture. So let's first I'll have 2 slides on some technical lemmas and definitions. So the first one, and this is what the algorithm depends on, is the so-called expected separable over approximation. So this is a tool which is used in the analysis of randomized algorithms which work with random subsets of things. These could be coordinates, this could be random subsets of data points, and so on. And the definition is that choose this random set valued mapping, the sampling as hat, any random subset, and then you have this inequality here which has to be satisfied. And that inequality, in this case, actually will be satisfied for some parameters vi's always. So this is not really an assumption. This is a definition of parameters vi's. Now you can stare at this for a while just to see what's going on, but I don't want to go too deep into this inequality. If you wish to understand a little bit more about this, you can look at some of these papers. This was the paper which introduced that inequality, not in this form, and this was a paper which only studied that inequality in the paper, nothing else. So the idea is that you have some quadratic here, but it's random, and you take expectations over some quadratics, and then you want to upper bound it by some diagonal or block diagonal quadratic. So that is really what's going on, and everybody knows if you have convex quadratic, you can always diagonalize it. So this is just a definition of what those diagonal elements should be, and they depend on these vi's, and these pi's are thrown in as well. Is a technical definition of some parameters vi's, and they'll be important for the rate. Okay? If vi's are small, the algorithm will be good. If they are large, the algorithm will not be good. Here's one example. If this S hat is everything with probability 1, so we go back to the primal-dual hybrid gradient algorithm, to the Schaumburg-Pohl algorithm, without any randomization, then this inequality is just equivalent to this inequality, and you can just choose these vi's to be all the same, and they're just norm of the C star operator. Okay, so that's what you can choose always. If you use just one coordinate at a time, I mean one dual variable at a time with probability pi, and that's what the sampling is, then you can choose these vi's to be just norms of these adjoints of the Ci matrices. And then this inequality will be true. So the idea is that whatever you choose, whatever sampling you choose, there'll be some formula for these VIs, and then you know what they are. Okay? So let's not look too much into this. And here is another technical thing which is using the proof. And this is a lemma which underestimates certain inner product, which is random, with something, and that something is supposed not to be too negative. And this parameter gamma tells you how much negative that can be. So again, don't look too much into the inside here, because there's not much inside you can get out of it. It's a technical lemma. The point here is that this is some inequality which we need to satisfy, and we need to set the parameter gamma in such a way that it will be true. And if this gamma is somehow large enough, then you can see that somehow this will work. Okay? Because then this is more and more negative and so on. And here's just an example of what this actually means. If you do the full sampling, this will in fact mean that this norm of this matrix has to be upper bounded by gamma squared. And this is coming back to one of those previous questions, how to choose S and T. So somehow what we have to do, we have to choose the matrix S and matrix T in such a way that norm of this matrix is upper bounded by gamma squared, and gamma squared satisfies this inequality. So it's at least the max of these VIs. So we have two inequalities that need to be satisfied, this one and that one.
But it needs too many iterations.
Pardon me?
It needs too many iterations to estimate.
So at the moment, we don't need to actually estimate this. At the moment, this is just a theoretical insight, which will tell us if you do this, it has to satisfy this. But you're completely right. If you wanted to compute this norm over this whole thing, then that's a lot of work. But fortunately, we don't really need the gamma parameter in the algorithm. It was not there anywhere. But we do need S and T, and we have to choose them somehow. So this is a cheaper way of doing it. You choose this S to be just multiple of identity, and sigma is the multiple, and you choose T to be multiple of identity, and tau is the multiple, and then everything simplifies, and this is what you have to satisfy. Okay, and now you have estimates of this norm, and practitioners would know what that is, and so on, and things are easy. But coming back to your question, now look at the randomized setting, because in the randomized setting, your question is much simpler. Because now we don't have to look at the norm of the entire big A, which contains all of those AIs, but we only look at the norms of these little guys, AIs. And all that we need is this inequality to be true for every I, but these little AIs, they're much smaller. The issue is that there's just many of them. So in fact, if you wish, you can go through the data once, you compute these norms at the beginning, it's just one pass through all the data that you have, and then you figure out what the gamma is, and you can choose the sigma is and tau. But this is a problem of all algorithms. Every algorithm has some constant that you have to fine tune. Even the basic gradient method has the step size that you need to choose, and theoretical choice is 1 over Lipschitz constant. What is Lipschitz constant? Well, it's just some norm of some matrix. So this is not unique to this algorithm. That's an issue for every optimization algorithm. All right, so there was some technicality, and now focus just on this box here. So this box tells you that the rate is 1 over k after k iterations. And this is the result, which is the generic result without the strong convexity assumptions. And the way we actually do this is in ergodic sense. So you look at the averages of all of those primal and dual iterates, and then you look at Bregman distances between those and the optimal points. And the Bregman distance is defined here, and it is done with the optimal subgradient here, P star. So if you measure the distances in this way, in an expected format, because these are random vectors, xk's and yk's are random vectors, then this original Lyapunov function, this big one here, which is just the distance to the primal, optimize the distance to the dual, optimizer, and some sort of a weighted average of these Bregman distances goes to 0 at rate 1 over k. Now, if you don't want to see a rate, then you can just see that these iterates, they go to 0 in Bregman sense almost surely. These Lyapunov functions are bounded in the expected sense, and so on. So there's some more insight that you can get into this. So let me pause here. So this should answer some of these questions about the rate of this. Yeah?
You open previous slide.
Sure. Here it is.
What is S power 1 divided 2?
So where are we looking? Here? No. Where are we looking? Here? Okay. So SI is a positive definite matrix, and 1/2 is the square root.
What does it mean 1 divided 2?
It's square root of the matrix. So you take eigenvalue decomposition of the matrix, and you take square roots of all the eigenvalues and assemble it back together. That's the square root of a matrix. So that's this. And pi, this is just scalar, so it's 1 over square root of pi. So this is some matrix. Again, I said this is a technical lemma here, so we don't have to look too much into it. I wanted to showcase it because this is where the VIs actually come into play. In this lemma, the VIs influence the algorithm through this lemma. And I wanted to highlight this a little bit. So gamma has to be at least the max of the VIs. Any more questions?
Without any strong convexity, yes?
This is without any strong convexity. This is just for closed, proper convex functions, Fi star and G.
Convergence in argument, not in function. Yes?
Yes, it's convergence in this sense. That's true.
But this sense
Yeah.
assume convergence in norm, because primal divergence is over estimated by the square of the norm. It is rather strange, because from this result we can conclude that we have convergence in argument without any strong convexity.
So what I would want to say that this is not in any way special in comparison with the Chambol-Pogge algorithm, because the red stuff is the new stuff compared to the Chambol-Pogge analysis. Okay, so this is nothing new that we're saying here, and this answers your question partially. So whatever they said, this is true here, but just in this expected sense. So you remove this red thing here, and that's what the upper bound would be here. You remove expectations, and that's the standard result. Yeah.
I understand.
Yeah, and let's leave that to later discussion.
Yes, okay.
So I'm happy to talk to you about that technical point. Okay, so from this theorem, you cannot really say what is a good choice of the parameter S and T and gamma and so on. I mean, theta is already chosen 1 because the rate is 1 over k, and somehow everything only affects this constant here, because the way you choose S and T will affect these distances, and you don't necessarily know what is a good way of choosing them, because you don't know x star and you don't know y star. So this theorem is satisfying in the sense that you don't need any additional assumption, and you get 1 over k, right? But it's dissatisfying in the sense that it doesn't really tell you how to choose T and how to choose S and so on. Then you have to experiment to see how things work, because it's difficult to estimate how that choice affects these norms, because you don't know y star, you don't know x star. Maybe there's an adaptive strategy that you can throw in, that as you go and you learn what x looks like, maybe you can adjust these T's and S's, but otherwise it's very difficult.
But if we consider the case when x star is not unique,
Yeah.
possible? Yes.
Sure.
So am I right that here we have to put such an x star that is the closest one to the starting point, if x star is not unique? What we should understand all of this x star in this formula, because it is not unique.
Yes, so I do not know from the top of my head. I will need to think a little bit. That's a very good question. Let's discuss this later. Yeah, that's a good question. Okay, so strongly convex case. So this is the case where everything is strongly convex. So we'll assume that G and Fi stars, they're all strongly convex. And now we have these parameters, mu G and mu I's of strong convexity for the regularizer G and the Fenchel conjugates of Fi's. Again, let's choose these parameters S and T in such a way that this gamma squared is upper bounded by 1. And these inequalities have to hold. Okay, so these look like very technical inequalities, but let me say that the theorem holds without all of the red stuff. That's the standard theorem for the original non-randomized variant of this method. So you just remove that, and we're just adding something extra. And if pi's are ones, then this disappears. This is just identity. So everything we just recover as a special case, the original result. So now, if you add these things, there always will be some theta so that these things could be chosen, so that these inequalities will be true. So that is something which, after a little bit of thought, you see, because you take identity, you perturb it a little bit by something positive definite. So obviously, there will be some theta which is smaller than 1, so that this is true. And then the same thing for this, so you just take the smallest of those, etc. So there is some choice. And again, we can spend a lot of time looking at these particular formulas, but let's just see what the rate is. And the rate is the theta to the power of k. And theta is smaller than 1. So you want the theta to be as small as possible so that these inequalities are true. And then that theta is going to be the rate. So looking at it this way, it's kind of difficult to see what's really going on. But you can look at it this way. And then it's much easier to see what's going on. So let's look at the very special case where we choose just one dual variable at a time with uniform probabilities. So it's 1 over n. Pi is 1 over n. And we define these condition numbers, ki's, to be the square norms of those data matrices ai's divided by the product of those strong convexity constants. And we choose t and si's to be just diagonal in this way. So we simplify our lives. Then you can choose sigma i's and tau's in this way. So I'm actually making a choice here. This is a very particular choice that I'm making. So gamma I can choose to be 1. So there's no problem. Then mu I, presumably I know. If I don't know mu I, then I cannot choose it. Okay? So if I have an explicit strongly convex regularizer, I can choose it. Otherwise, it's difficult. Ki, well, I probably know because I know strong convexity of G and strong convexity of Fi star, and I know this norm. I can compute it. If I know this, I can choose this parameter. If I don't, I can't. The same thing with tau. I just choose it in this way. It uses the same parameters. And then the rate is this. 1 minus 1 over this form. And the reason why it's written 1 minus 1 over something is because this stuff in the parentheses is really the complexity. That's the number of iterations you need. So from this, you conclude that the number of iterations you need is n plus, and remember, n is the number of dual variables, plus n times maximum of the square root of these condition numbers. And this is really 2 times gamma, and gamma is 1. So thing of gamma is 1. Okay, so this n plus means you have to at least take 1 pass over data, or you cannot solve this problem. And if the condition number is large, then it's really n times max of the square roots of these condition numbers. Okay, so now let's do important sampling. And this is why these probabilities matter. So now we will not choose these probabilities uniformly, but we will choose them in this way. So proportional to the square roots of those condition numbers. If we do it that way, then in fact everything is much better. So we make this choice of parameters, and then notice that this term n changes to sum divided by max. So it's upper bounded by n. It can be much smaller than n if this sum is much better than n times the max. Okay? So it's all about the distribution of the condition numbers. If the condition numbers are not uniformly distributed, then this is much smaller than n, and this will be much better than the max, because you notice you have n times max, and here you have some of these things. So we are replacing maxima by averages. And this is usually what happens with important sampling in randomized optimization, wherever you look. Maxima are replaced by averages, and if averages are much smaller than maxima, the randomized method will be much better. Okay, so let me pause here. So, and I want to ask questions. So we started late. Can we also finish late? And if yes, then when?
Of course.
And when? Because I don't remember when we started.
Still about 5 minutes. 5, 6.
So we started like 6. Oh, okay. Okay. There was a question.
About it is required to calculate condition number of the matrix, which is the capital. And is it possible to implement that important sampling in practice?
Important sampling. Sometimes yes. So the answer is not, I would love to say that the answer is just yes, you can always do it, but it's not true. Sometimes you can do it, and you can do it if you can actually compute these guys. But if you cannot compute these guys, it's difficult to choose even sigmas and taus. Okay?
What to do?
Pardon me?
What to do?
What to do?
Yes, I cannot calculate.
If you cannot, then one thing to do is to estimate, because you can do the analysis with upper bounding the condition number. You can estimate. But this is, again, I want to say this is not a specific problem of this algorithm. This is a problem of every single optimization algorithm which has a step size. Right? You can equally ask me, how do I estimate the Lipschitz constant of the gradient? And we can get into business talking about this, but this is a classical question. And it's about estimating really the largest eigenvalue of the Hessian and so on. I mean, that's what it is about. Okay? So this is not specific to this. In fact, if anything, the task is easier here because we only have to compute these condition numbers of smaller matrices. Yes?
I guess the real problem only is the strong convexity parameters, because
yes.
in the norm of the matrix you can use
yes.
some kind of
yes.
Arminto,
yes.
Nesterov technique.
Yes, definitely. Yeah, definitely. So if you don't know, and there's many practical instances where you don't know mu I, okay? You just don't know it. And if you don't know it, then this recipe would not work well.
You can use
okay?
start on this parameter.
Yeah. Or you can use the algorithm before, which it doesn't have to actually use this. And you get the 1/k rate. I mean, there's some things you can still do. And I have experiments where we make some of these choices. Good. So I will not go through the details of this algorithm. What I want to say, though, is that this is the dual acceleration. So you do acceleration in this step. So what happens then, instead of just single sigma, now you have a sequence of sigma parameters, and you choose them in a very specific way. So you update them here, and you update them here. So once you do that, whatever that means, and again, we can spend just 10 minutes on the slide. If you do it this way, if you adaptively change these step sizes for the procs of fi star in a very specific way, so they will not be constant anymore, then the rate that you're going to get is 1/k squared. And again, you can ignore everything. Just look at this box. You get c/k squared, and you get this with respect to this initial constant c. Okay, I'm not actually showing it, but and this is the initial error. This is not something that holds, though, from the first iteration. But it's also not an asymptotical result, because this k0 is actually quite small in practical applications. And again, if you remove the red stuff, you get the result for the non-randomized Champollion algorithm. So at this point, I should probably show at least one numerical result. I have probably 20 slides of numerical results, but let me just show a few. So here is one. Here is where we work with the TV regularizer, but we make it strongly convex by adding this little regularizer here, because we want to make it strongly convex. We want the mu g to be positive, and we enter the mu g there ourselves. We enter some number there, so now we know mu g. So that issue disappears, and we use some modified KL divergence here. I don't have the time to get into the details, but let's look at what happens in computational experiments. You do 5 epochs, and by 5 epochs, I mean you 5 times look at all the data that you measured, only 5 times. So this is equivalent to 5 gradient iterations, so to speak. So this is our best estimate of the true solution by running the algorithm for like way too long. This is what the Champollion algorithm does after 5 iterates, and this is what the randomized one does when we choose 20 of these blocks. When we choose 150 of these blocks, so the lowercase n is 150, then it's even better, even though it's probably not that visible here, but it's a little bit sharper. So the difference between the randomized and this one is just really, really huge. And this is what you normally see also in some other plots. You look at, let's say here, the distance to saddle point. And you see that the non-randomized one, which is this one, converges like this. And now the uniform sampling randomized one converges much, much faster. These dashed lines are theoretical upper bounds. So the theory is quite tight in this example. Okay, so the difference between this and this is really big. Now, how many more minutes do I have?
2, 3.
2, 3, okay. So in 5 minutes, you tell me 1 more minute. Okay, good. So you can see that also if you look at the signal to noise ratio, which is something that matters, the way this increases with the number of epochs for the Shambo-Pog algorithm is this, and it's much faster for the randomized algorithm. And the reason is really the randomized algorithm learns much faster. It makes many silly steps, but by the time it makes one pass, it learned a lot and much more than one step of the original PDHG algorithm. And now you can look at it from a different perspective. You can look at the objective function value. So things are better for the objective function value, and so on. And then I have lots of other experiments, but I will probably just stop here and allow you to ask some questions. Maybe I just show, I'll just stop on this slide here, and I'll stop. Thank you.
What is the size of matrix in your?
Pardon me?
What is your matrix size?
Oh, so that's yeah. So that's a good question, but I'm afraid I don't quite have the answers. Yeah. So I don't remember. I really don't remember. I'm sorry. So I didn't do the experiments, and that's why then you got a little bit detached from the numbers. So these problems, but I don't want to make the impression that these are really huge problems. These problems are not that big. In the second paper that I mentioned in the beginning, we actually applied this to real PET data, and there the problems are much, much bigger.
F star is a networking function, yes, or just simple logarithmic function in this application?
It's not that simple. It's a modified one.
So this is a logarithmic function, or
Yeah. There's logarithms in there, but it's a special generalized entropy thing, and we modified it also a little bit. I can show you the exact formulas.
Okay, maybe one more question. Okay, let us turn the speaker once again.
Thank you.